Hello guys, in this lecture I'm going to go over an important topic in our course, which is robot singularities. Robot singularities are regions in the robot workspace on some particular values for theta 1 and theta 2, where the robot is unable to move in a particular direction or can move in one direction more than another. What we'll do in this lecture is we're gonna be able to calculate the angles, for example, in this 2 degrees of freedom robot, the angles theta 1 and theta 2, where this robot have a singularity. To begin, we'll begin by looking at the forward kinematics of this robot. And the forward kinematics of this robot is, I know the coordinate of my vector, xe is equal to L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. We have derived that in a previous lecture. And ye is equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2, where obviously L1 and L2 are the link lengths on this robot. Now, if I differentiate my xe and my dy basically to obtain my Jacobian, we know my dx is going to be equal to dxe, or the partial derivative of xe with respect to theta 1 multiplied by d theta 1 plus the partial derivative of xe with respect to theta 2 multiplied by theta 2. So this is my Jacobian. And if I go ahead and I do the calculations, I'm going to end up with dx over d theta 1. It's going to be equal to minus L1 sine theta 1 minus L2 sine theta 1 plus theta 2. Now, dx d theta 2 is equal to minus L2 sine theta 1 plus theta 2. And on the row here, we have partial derivative of ye with respect to theta 1 is equal to L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. Last term, partial derivative of ye with respect to theta 2 is equal to L2 cosine theta 1 plus theta 2. It's missing a parenthesis here. So let's look into singularities, and what I'll do is I'm gonna hopefully introduce that by virtue of doing an example. So if you look at the situation of this robot where theta 1 is equal to 0 and theta 2 is equal to 0, well, this is going to result in a flat position of the robot. So this is my theta 1 and this is my theta 2. And then if I obtain the Jacobian at this position, and we know that the Jacobian will basically depend on whatever position that the robot is, so the Jacobian will always change. So we know J is equal to minus L1 sine theta 1, so theta 1 is 0, so sine of 0 is 0, minus L2 sine theta 1 plus L2, so this guy is 0. Here we have minus L2 sine theta 1 plus theta 2, so this is also 0. And in the second row, we have L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. So cosine of 0 is 1. So we're going to have L1 plus L2 here, and then we're going to have L2. So based on this configuration, we know that the first row of the Jacobian is all zeros. We have 0 here and then 0 here. If we plug that back into our initial relationship for the Jacobian, which relates a small displacements in theta to some Cartesian displacements along the x and dy, we see that dx is actually equal to 0 d theta 1 plus 0 d theta 2. And dy is equal to L1 plus L2 multiplied by d theta 1 plus L2 multiplied by d theta 2. So rewriting that, so we're going to end up with dx is equal to 0 theta 1 plus 0 theta 2. So what is going on here? So what is actually going on here is at this particular position, no matter how the motor on link 1 changes, and no matter how the motor on link 2 changes, so regardless of the variations that we're trying to move the links, we are actually unable to move in the x direction, right? And it makes sense, right? So if we are here, no matter what kind of fluctuation you try to do over here, right, on theta 1 to the 2, you just can't go in the x direction. You may be able to go in the y direction, but you can't go in the x direction. So in this case, what we say is we have a singularity in the x direction. Why do we have a singularity? We have a singularity because no matter how theta 1 or theta 2 changes, we cannot go in the x direction. So essentially, we have a mechanical lock on the system, and this is called a singularity. Regarding dy, so yes, we actually can move it, right? So if d theta 1 is positive, then we know we can move dy. And likewise in this case, right? So dy will actually move whether the theta 1 changes or the theta 2 changes, right? Which makes sense. Looking back again at the robot, if the first link moves, this guy will go up. If the second link moves, this guy will go up. If both of them move, we'll have a compounded addition of the angles. All right. Again, so robot singularities is a direction about which the robot cannot move, and then you will be able to see that when you have a row in the Jacobian to be 0. And what else do we know from here? So if you have a row in the Jacobian to be 0, it simply means that the determinant of the Jacobian is actually 0. So the quickest way of actually knowing if you are near a singularity or not is by computing the Jacobian. And if the calculation of the Jacobian leads to 0, it means that you have a row that is actually 0. Okay. Now let's look into another situation where we could have a singularity. Let's consider a situation where the robot is in a vertical position, where theta 1 is equal to 90 degrees. And this is my theta 1 right here. And my theta 2 is 0. If you recalculate the Jacobian, we know it's going to be minus L1 sine pi over 2 minus L2 sine pi over 2. So we know sine of pi over 2 is 1. So this guy will be minus L1 minus L2, and this guy will be minus L2. And here we're going to have 0 because cosine of 90 is 0. So we have a row of zeros. So here, if we look into this again, we will see that we can have displacements along the x, but we cannot have displacements along ui because both of these components are actually 0. So no matter how the theta 1 changes, dy will always be 0. So we have a singularity in the y direction. Now looking at dx here, we see that if theta 1 changes positively, or if the motor or link 1 moves positively along theta direction, then we know dx will actually go in the opposite direction because of the minus, right? Which makes sense. So if d theta 1 grows by a bit, right? So this is d theta 1, and then likewise d theta 2 grows by a bit, then this guy would be like this, right? Then we are definitely going in the opposite of the x direction, right? So this is my x and then this is my y. But what we're trying to say here is that we will have a singularity in the y direction. All right, now using the Jacobian, we can tell whether we are in a singularity or if we are not in a singularity. But how do we know if you are close to a singularity? Let's say the robot is in this configuration. Let's say the robot is like that. Is this near a singularity or not? Or we know this is for sure a singularity. The fully horizontal one is a singularity. But what about this guy that is slightly inverted? Like, how do we know the region of a singularity? And one way to do that is basically by doing a mapping between the joint space, right, and the Cartesian space. Here's how we'll do that. So what we will say is that assuming that so the robot is at any position, right, where you have here like theta 1, and you could have theta 2. If you try all the possible configurations, so this is theta 2. So if you essentially try all the possible variations of d theta 1 and d theta 2, you will actually see that you will actually have a circle. So a circle over here will basically map that d theta 1 has moved from the minus direction and then the positive direction, and then d theta 2 have moved from its minus to its positive. So we can see how we can map this circle, which is in the joint space, in the Cartesian space. All right. So again, this circle is a full mapping. So if you are moving all thetas, right, how will your Cartesian position actually changes? All right. And that is the importance here. So we're looking at all the possible configurations of the thetas, and then we'll see that implication over here. So we're trying to map a circle in the joint space into the Cartesian space, and then we're going to see how that looks. So what is the equation of a circle? We know the equation of a circle is d theta 1 squared plus d theta 2 squared is equal to 1, where 1 is the radius of that circle. I can put that in matrix format by doing the transpose. So this will be d theta 1, d theta 2 as a horizontal vector multiplied by this guy, d theta 1 dot and d theta 2. This is actually equivalent to the transpose of d theta. right? Where d theta is equivalent to d theta 1 and d theta 2 as a column vector. So d theta transpose multiplied by d theta is equal to 1. So this gives me this equation. But then we also know that d theta is actually related to dx, right? We know that d theta is equal to the inverse of the Jacobian multiplied by dx. So again, we're trying to have, so we started by having a pure circle in my joint space. So each joint is moving, in all its possible directions. Let's see what happens to my Cartesian direction, this direction. So we do that, then we know d theta is equal to j minus 1 dx. So we replace d theta by this guy and we plug it here. So d theta transpose, when you do a transpose of two matrices, then it will be flipped but transposed, right? So dx transpose multiplied by j minus 1 transpose. Then what we can do is we're gonna end up with so we have d theta times d theta transpose times d theta. So we'll replace d theta by its value, which is from here. So d theta is going to be equal to dx multiplied by j minus 1 transpose, which is here, dx multiplied by j minus 1 d transpose, multiplied by d theta, which is equal to this guy, which is here, right? So this term right here is d theta, and this term right here is d theta transpose, all right? But ultimately, I'm going to end up with dx transpose multiplied by some matrix here, which is called A matrix, where A is equal to J multiplied by JT, the inverse of that, minus 1, multiplied by dx. All right. So this is actually the equation of an ellipse. So dx transpose multiplied by some, square matrix multiplied by dx, where dx has to be obviously 2 by 1, it will actually give you an ellipse, right? And what we will actually call is that this is a manipulability ellipsoid. So this ellipsoid will essentially define the mapping of my thetas. All right. So I'm starting with a pure circle here, like all the possible configurations or all the possible rotations of theta 1 and theta 2. I want to see how that would look like in my Cartesian space. Let me show you a little bit more about how that would look like. So this is what I had, dx transpose multiplied by A multiplied by dx. And then we said the equation of this guy is an ellipsoid. So how does the ellipsoid would look like? So this is the ellipsoid, and it turned out that the major axis of the ellipsoid, right? So this is a major axis. So the major axis of the ellipse will actually runs along the first eigenvector. So the V1 is the eigenvector of this matrix A, right? And V2 is the second eigenvector, and this is a minor axis. All right. So V2 is a minor axis, which is the second eigenvector of this matrix, and the radius or the length of this guy is actually square root of the eigenvalue of this guy. All right. So square root of lambda is the radius of the major axis. So this eigenvalue is associated with this eigenvector, and this eigenvalue, lambda 2, is associated with this eigenvector. And the square root here of the radius is a little bit just symbolic to show that, you could probably take this off, and then because the concept of the manipulation ellipsoid is abstract in a sense, just to show you what happens, for the robot and how could the robot move basically at any given point. And to calculate the eigenvalue, this is from your linear algebra course. Obviously, you simply do determinant of A minus R lambda, and then you can solve lambda, and then you can solve the eigenvector. I will show you how, in this course, we're going to do it in Matlab. Just to tell you a bit about how that would look like. So if this is my robot right here, so if the robot is here, how do you think my manipulability ellipsoid here? Well, I have a singularity in the x direction, right? But the robot can move along the y direction. So my ellipsoid is actually going to look like literally like a flat line, right? If you look, so this is the ellipsoid, but the radius of the ellipsoid in that direction is 0. Okay. If this guy is here, then you will actually have, maybe something like that. Why? Because you can have more velocity in that direction than in that direction. All right, and we're gonna basically use Matlab to do that. So all we do is basically we know A, and what was A? A was equal to, so you get the robot, then you find its Jacobian, then you find A, which is equal to uh, J multiplied by J transpose multiplied by -1. So once you get A, you go into Matlab and you can use this relationship. So UV is equal to eigenvectors of A. And what that will actually return is that U are the eigenvalues of matrix A, and then V are the eigenvectors of this eigenvalues. So V will be, so U is going to be like that. So lambda 1, lambda 2, etc. to lambda n. So lambda n is the number of degrees of freedom. In this case, we have 2 degrees of freedom, so it's only lambda 1 and lambda 2. And V is going to be equal to the first vector, right? So I want to call it V1, V2, V3, down to Vn. All right. So in our case here, so this guy could be, you look into the first, so this is a radius, and then this is a vector. And the vector here is going to be, let's say, this is my V1, and V2 could be like that, right? So in this case, we only have 2. So V2, lambda 2 is going to be the radius of this guy, which is this length right here, or the square root of lambda 2. All right. Okay, let's go to Matlab and then I can show you the example. Oops, not here. Just a second. Okay, so this is Matlab, and this is, by the way, an online version of Matlab, which you can also access. What I have here is that this is the example that we have. I have L1 is equal to 1 in this case, just some arbitrary link classes on link 1 and link 2. And these are my thetas. Theta 1 in this case is power 4, theta 2 is 0, and the J is my Jacobian. So we've already calculated our J. Right, you can do this by hand, or you can do it also in Matlab using the diff function that we spoke about. So this is simply my Jacobian. And A is the value, the matrix that we just defined, and V and U are our eigenvectors and eigenvalues. I think I mistakenly, so these should be swapped. So it's V and U. Okay. In Matlab, if you want to understand the function, just type help, for example, Eig, and then it will actually, do all the documentation for you. It will kind of like, walk you through it. Okay, so this is V and D. It tells me that, V is my eigenvectors, right? And then my D is eigenvalues. Okay, so simply I'm solving V and then U, and then I'm plotting it. And the way that I can plot it is, let me first stop my video, all right? The way I can plot is as a line, right? So because I know my V matrix, basically, this guy, basically, it has the eigenvector. So I can use basically the line function in Matlab to be able to plot the vector as a line. Okay, so it's really, really simple. So I'm gonna run this, and when you run it, you can just hit F5. And what I want to do first is let me actually show you the output of this function. So I'm going to run it. Okay, let's see. So what I'll begin is, let's actually begin by 0, 0, because we've already run that. So if I'm at 0, 0, what do you think is going to happen? Okay, so if I'm at 0, 0, then my V, right, which is what? My eigenvectors, right? So the first eigenvector, so the first unit vector, which is shown here in red. So I'm plotting the first eigenvector in red and the second one in black. So the first eigenvector has a x coordinate of 1 and then a y coordinate of 0. So this is my 1, 0. It's in red. And the value that is associated with that is here. So we said these are columns of eigenvalues. So 0 is the radius. So we see here, basically, we have no ability to actually move in that direction. So that is why my radius is 0. And in the second direction, 0, 1, how much can I move by 0.2? So I can actually move a lot. So my ellipse is basically along the major ellipse of the major axis of the ellipse is along this direction. Now let us change this to, let's make theta 1 to be pi over 2, and then keep theta 2 to be 0, and rerun that. If you do that, then what are you getting? So the first vector is how? So this is my first vector is okay. So the red one is first, so it has x coordinate of 0 and then -1. Okay, so this is my first axis, right? And which is a vertical direction. And what is the radius that I can move in the vertical direction? How does the robot look like now? By the way, the robot is in a vertical direction. If it's in a vertical direction, it has a singularity along the y direction, right? So -1 is basically, x is 0, -1 is the y. So this is this vector or the vertical direction. And it doesn't matter if it's -1 or +1. It means this is a positive direction or the vertical direction. And the radius is 0 basically because we can't really move along this direction. It's a singularity in the y direction. Now, if I look into the other eigenvectors, it's -1, and there you have it. So this is my -1. Okay. Now, what I want to do is I want to actually do pi over 4. So if I were actually at pi over 4, it means that my let me actually draw this very quickly just to make sure that we are all on the same page. So if it was pi over 4, then if the first one is pi over 4 and the second one is 0, then this is where we are, right? So this is my theta 1 is pi over 4, and then this is my theta 2. Let's see what happens here. So if you run that, you will see that I have an eigenvector that is 0.707 and then 0.707. So I have something like this, right? Is in the opposite direction. So this is my first vector, right? And then the second direction is that it has actually a positive x and then a negative y. So it's actually like that, right? And what is the radius associated with the first eigenvector? The radius is basically 0, right? And again, in my U in Matlab, basically it returns lambda 1, lambda 2, etc. So, right? So as you go from here, basically this is your first radius, your second radius, etc. So this is the radius associated with the first eigenvector, which is this guy. So how much can I move? What is the radius lambda 1? It's 0. Why? Because I cannot actually move in that direction. There is a singularity along this eigenvector. In the other direction, actually, I can move. Okay, so you will actually only be able to see the second radius is that if your other theta is any value. Let's just put 0.3. If you do that, you'll actually see that you actually have two radiuses, right? And here, basically, we can move in these two directions. I can move in this direction way more. This guy is 56, way more than I can move in that direction. So it will kind of tell you when you are using this manipulability ellipsoid, it will actually tell you in which direction you can actually move a lot more. And then, but the direction is in the frame of your eigenvectors, right? It's not in the frame of your main XY frame. It's in the frame of your eigenvectors. Okay. Okay, now what I would like to do is the other thing that I want to go over is actually it turned out that there's another interesting relationship of this, which actually occurs in the forces. So I also know that my dx is equal to the Jacobian multiplied by dq, where dq is basically equivalent to d theta, right? So this is what I mean, dx is equal to j d theta. And I also know from one of the previous lectures that my torque is related to the force, right? So the torque on the motors is actually related to my Cartesian force, Fx and Fy by the Jacobian transpose, right? So if I know some forces that this manipulator is applying, I can actually calculate the torques based on that relationship. What I'll do is I can actually also try to, do a similar mapping. So if all the motors are applying torque, so if motor 1 is applying torque T1, motor 2 is applying torque T2, and I'm looking into all the situations, what happens to my force, right? So I can also actually get a manipulability ellipsoid for the forces. And then by using this, I can also tell now in what direction the robot can apply the more force, all right? And the way we do this is, first of all, we're going to define what I mean by the circle. The circle is essentially T1 squared plus T2 squared. And And I can write that as, torque transposed multiplied by torque, where the torque is what? Is a vector, right? Of T1 and T2. So this guy will give me that relationship. And I know the torque transpose is related to the force by this relationship. So I can write that here. And then torque is equal to JT times F. I can write that. So now my FT transpose equal to JJT multiplied by F is equal to 1. So then I can get another matrix here. It's actually the inverse of A. So JJT is actually the inverse of A, which we calculated for the position. So long story short is because the eigenvectors are orthogonal, right? It turned out that the eigenvectors of the inverse matrix is actually orthogonal to the original matrix, right? So if you get lambda 1, for example, in one matrix, and you get lambda 1 of the inverse of that matrix, basically lambda 1 will be the inverse of the other one, and the eigenvectors associated with the first lambda 1 is actually orthogonal to the eigenvalue of the new matrix. To explain that more simply is that, let's say you initially calculate the position singularity or the position manipulability ellipsoid that was spoken about earlier based on A, then my force is actually simply is very perpendicular to that. So it will be another ellipsoid that is perpendicular to that. And it makes sense. So you remember here we had a singularity in the x direction, meaning I can't move in the x direction, but I can move in the y direction. So this is my position manipulability ellipsoid. And I can actually apply way more force in that direction than I can apply in this direction because of the toggle position, right? So if the manipulator is like that and it's stuck, for example, on a wall, it can apply way more force in that direction, right? Then it can actually apply in this direction for the same torques, right? You can apply basically way more force in that direction than it can apply in this direction. And this is the first force manipulability. So this basically tells you, the directions in which the robot can actually apply more forces. So this is a very important concept. What really changes is simply, as we were calculating before. So if I quickly go back to my Matlab script, you see basically my A was equal to the inverse of J multiplied by J transpose, right? What actually will change is that instead of the inverse, now it's basically that, right? So now we're actually looking at the eigenvalues of my manipulated ellipsoid. And you see that basically the colors have changed. Basically, we just swapped the eigenvectors. What I'll do is actually I'm gonna post this on Blackboard. So that script is gonna be, I'll post it on Blackboard for you guys to also see it as well. All right, one of the last things that we're gonna describe in this lecture is gonna be, I'm gonna go back to our class presentation and make sure you read and then do the exercises in my class presentation. So this lecture basically kind of goes over all of this. One thing we can define is that how far we are from a singularity is you simply divide the radiuses of this ellipsoid, and if that ratio is close to 1, then you basically have a circle, then you are very far from a singularity. All right, and this is how you can define that. And okay, so if k is equal to 0 or infinity, we're approaching the singularity. Why? Because k is the radius of a radius. Is a ratio of these two radiuses, right? Either if lambda of 2 is 0, or if it's infinity, it will actually dictate the value for k. So make sure you do that. I have a very small example here. Again, so I ask you, for example, to find the ellipsoid for particular position of the robot, and you have to find the eigenvalues, and I'm pretty sure most of you know how to do that, and you are expected, because linear algebra is a prerequisite here, that you have to know linear algebra. Very basic matrix manipulations here. So all you do is to find lambda, find the absolute value of, or find determinant of the matrix minus lambda, and then you can solve for lambda. And then once you solve for lambda, you replace it here in the initial equation, and then you can find the eigenvector of that. You can use Matlab, or you can for our exam, I'll let you guys use Matlab to be able to find the eigenvectors and eigenvalues. And this is what we did in terms of the torques here, right? So this is a torque, and this is my this is the previous relationships that we calculated, and we came up with that relationship. And then here we said that The force ellipsoid is actually perpendicular to the velocity ellipsoid. And here, basically, we have different scenarios that you can, look on. This is what we just did in Matlab. All right. Yep. So there's another script basically here, so you can also do that script also as well. So this will also do it for you. Okay. So there is one last thing that we're going to discuss here. So last time we said that knowing the Jacobian, right, or calculating the pseudo inverse of the Jacobian, we can use that to iteratively solve the inverse kinematics of a robot, right? Why? Because with that, we know that dx is equal to j times d theta. We know d theta is equal to j minus 1 dx. So if the robot was at any position, right, I can write a loop, right, and I can reiterate the loop by saying that theta is equal to the initial theta plus d theta, where what is d theta? Where d theta is equal to j minus 1 multiplied by dx, right? What is dx? Dx is equal to some very small value, 0.01, for example, multiplied by the x desired minus your current position. So if this is my dx, right? So the code will start like that, right? If it was a Matlab code, so I'm gonna do like, let's say 4, right? What we will do is, let's say I have, so d theta is gonna be equal to j minus 1 dx, right? But what is dx? Dx is equal to 0.01 x desired minus x, right? X desired is any value. Like let's say you're trying to solve the inverse kinematics of this vector xd, which is, let's say, like in the case of the degree of freedom robot, 0.5 minus 0.5. You're trying to find what is theta 1 and theta 2 that would correspond to the robot being at in this position, for example, 0.5 here, and I have minus 0.5. Okay, I'm trying to find what is the value of theta 1, what is the value of theta 2. Okay, so I can find, so this is my desired x, right? And then this is independent of the DH parameters, by the way, here, right? So here, whatever fluid kinematics you are using, right? This will work on it. So this is my dx, right? So I have my x desired. We need to start with some initial values for thetas. So from the initial values, we can get x. We know dx, we calculate d theta. Then from d theta, we can say theta is equal to the previous theta plus d theta. Once I have the theta, I can actually get S is the fluid kinematics of theta, right? And then the loop will basically recycle. So let me just quickly do that. So the loop will actually come back here, right? So you calculate X from fluid kinematics, you calculate a tiny step dx, which is x minus your x, you find the theta, you find how much the absolute theta has changed, you use fk to find, based on this theta, where is the robot right now, then you come back to your error, etc. So you keep doing that, and then the robot will actually ultimately solve this inverse kinematics of the robot. So this is based on j minus 1. Okay, it turned out that I can actually replace this j minus 1 by another way, which is called, you can use d theta is equal to j transpose dx. Simply, so instead of doing the p inverse of j, you can actually do j transpose dx. And if you do that, this is called the Jacobian transpose control. So in the previous case, let me plot it a little bit bigger. So let's say the robot is here, and I'm trying to solve the inverse kinematics of this point. So in this case, basically, if I were using j minus 1 to actually do this iteration, and if I was actually tracking x, where x is, so let's say you started from this point, you will see that the robots actually will go from here to here along straight line. So it will start here, and then it will actually solve this. If you replace the, j minus 1 by j transpose, you will see that this guy will actually come like that. So this is solving the solution. So j minus 1, solve the solution in the Cartesian space. But if you use a Jacobian, you actually solve it in the joint space. And then this is why it's basically like a curved motion. And then here it says, so here using J minus 1, here you are using J transpose. So, you know, Jacobian, even though it's a very simple concept, but actually has just a lot of applications in actually robotics that, you know, are very important. And then why that works, why this works is because of this derivation. And obviously, I'm not making you guys responsible for knowing this. This is a graduate level stuff. But you know, if you start with an error, if you define the error to be, you know, your reference minus x, error is equal to 1 over 2x, error minus x xt times x error. If you actually take the partial derivative with respect to theta, you will see that you will end up with partial derivative of e. It will actually be this. So this is basically differentiating this matrix, right? So the easiest way to realize that is you can kind of populate this, or you know, do a small experiment in a 2 degrees of freedom robot, and you will see that this actually works. What happens is that so this is the derivative of the error with respect to theta, right? Now, if you change your theta to reduce the error, so if you take steps proportional to alpha in the direction of the negative gradient, you will actually see that so q prime basically is going to be proportional to that. So I can write q prime is actually equal to alpha times this guy, right? So I'm taking steps in the opposite direction of the error. So here, so this is my q prime. You will see that you actually end up with this term dx over dq. What is dx over dq or dx over d theta? Partial derivative of the x with respect to is actually the Jacobian. Right? So you'll see that this term actually ends up being equal. So you don't need to know this derivation, but you need to know so this, right? So we have two methods for actually calculating the inverse kinematics using the iterative method. The first way is using the pseudo inverse, and then this will give me a straight line from the current position to the point that I'm solving, and then the other method is using the Jacobian transpose, and then this will actually give me that. Okay, guys, so there will be more assignments on that. It's very important that you fully understand that topic of the course. Any questions, guys? Please never hesitate to send me an email. I'll be very happy to set up Zoom calls with you guys, or by email or whatever. At any time, Zoom works best for me. So anytime, I'm usually available in the afternoon. I'd be very happy to jump on a call and then really explain anything that you guys want. Yep, that's it.